Welcome in. Let's do a summary of all the derivatives that you run into. And in particular, I'll concentrate on parent functions that you have studied kind of throughout. So if you've done functions and then you've got yourself into calculus, this is kind of a full-out summary. It's one of the last videos that I'm doing with respect to calculus, and then I'll be probably moving on. And in this video, so what I want to be able to do is I want to go through all of these parent functions. You should be able to characterize them so you kind of know how they look like, how they act. If you date yourself back all the way to grade 9, you have studied these. So, a constant function, you've certainly studied y is equal to x. So basically just a line, you can manipulate that particular line with slopes and y-intercepts. You have studied quadratic functions, so that's your x squared. You've done quite a lot of that. You can move that around with various transformations. You have studied cubic functions, so x to the 3. So those ones kind of date you back quite a bit. Now, finding their derivatives, we're going to take a look at that, and I'm sure that as you're summarizing, you should be able to know these as well. Then, your general power function. So of course you can go x to the 4, x to the 5, and you can keep going. So what is the derivative of any power functions that you have? Okay, then you have kind of an inverse, so 1 over x, function. So x cannot be equal to 0 there. So what is the derivative for that function? And then again, so generalize it to any inverse, so basically a power function in reverse. So 1 over x to the n. Then you kind of shift over. At some point you must have done the absolute value function, which kind of looks like a v. So there is that particular function. It's defined everywhere, but the derivative is not, so it's not defined at 0. So I'll take a look at that. And then you have all your trig or sinusoidal functions. Really, you only have to kind of think about sine, cos, and then from sine and cos, you can derive everything else, which is what I typically do. I be honest with you, I forget all the other derivatives that you have, even 10x. I know what it is because I'm making the video, but in reality, I just try to remember sine and cos, and then the rest I do derive. So for instance, cosecant, secant, and cotangent, I can't remember. So I will typically derive it. You as a student in calculus, you probably will remember because you're going to be doing it over and over and over again. When I teach, it does come back to me. And when I make these videos, it certainly does. But I'll do it from kind of first principles and show you, I'll put these in green. They're not really necessary if you know your sine and your cos. And, from there, you get into your exponential functions. So e to the x, which I think is really crucial. Unfortunately, I don't know how heavily it is covered in calculus and even in your functions. E to the x, you typically will do any exponential, generalize it. But e, so Euler's number, is really crucial. So I like to separate that particular base. So the general one is b to the x, where b is between 0 and 1, or it is greater than 1. And then you kind of finalize, you can do, your logarithms. So again, the general one is log of any base of x. But once again, because of the Euler's function, so the ln of x is a super important function for us. And we should know what its derivative is. It's actually rather simple. Now, I have derived all of these. So, if you want, you can certainly go on my site and you will find, so 1mjourney.com, when you click on the math button, I have done every single course pretty much in high school. As I'm kind of finishing up the calculus, you'll find all of this information there. Now, what I have done is I have summarized all of these, not just in video form. I have made a table. And in this table, I am very specific. I also tell you, where these derivatives are defined. And I have done all of them. So in a nice, very kind of one-page table, as you can see here, with all of these provided and the derivatives on the right-hand side. I'm going to go over those in the video. Now, if you will want to see or download this particular document, you can go and open the show notes there, expand it. Okay, you'll find the link. It's for free. You can download that one-page document for yourself to have it handy whenever you do need it. And once you know all of these, well, you pretty much have calculus in your pocket, okay, at least with respect to derivatives. Then it's just a matter of learning all the applications, which you probably have gone through if you've been watching these videos with me as I've been creating them. So let me go back and let's do a deja vu. So let's kind of take a step back. So all of these derivatives, I'll go kind of one by one. So the constant, well, the derivative for all x is basically nothing but 0 because our function is just a flat line. So that is the derivative, okay, of any constant that you have. The second one that you have in there, so if you take a line, so it should not surprise you. So the derivative here, okay, which basically means the slope is going to be equal to 1. And that one, okay, is just nothing else but the slope for all of x, okay, because it is just a simple line which crosses through the origin. The next one, which is your quadratic function, so this is your parabola, okay, so famously touching at the origin, okay, and then spanning upwards. You can then change it any way you like it. So this particular parabola, the derivative is 2x. And that is defined for all x everywhere. Your cubic function, so x to the 3, okay, which kind of looks like a nice squiggly, okay, up and down that you have it. So this parent function, if you take its derivative, is equal to 3x squared. So it does become a quadratic, okay, so it's a parabola in terms of its derivative, okay, so that you actually see there. And it is defined for all x. There's nothing special happening to this. Your next one, which is your power function, okay, so x to the n. So this one, you always drop your n to the front, you multiply it by x, and then you take the exponent and you subtract 1 from that. So that's what you have it, okay, with respect to this derivative. Now, the next one, okay, in terms of 1 over x, so kind of the inverse that we would have. So in this case, if you take this one, you can rewrite this function. So you can certainly write it as x to the negative 1. And if you do have it that way, then you can use the general power, okay, which will be that the derivative is just simply negative, and this will be x negative 1 minus 1, which is going to be negative 2, which equals, if you rewrite it as a fraction, so this is going to be, or in fraction format, it's going to be negative 1 over x squared, and that becomes your derivative. And of course, it cannot be defined at 0. So that is what you would see there. In the general case, so if you take 1 all over x to the n, so this one, again, just from power functions. So if you recall, this is nothing else but x to the negative n. And if you take its derivative, then its derivative is going to be negative n, which drops to the front, multiplied by x, negative n minus 1, and that is your derivative. And you can simplify this a little bit further, so it can be negative n. This is going to be x negative, and this is n plus 1. And if you rewrite it in fractional form, so this is going to be negative n all over x to the n plus 1. And that becomes your derivative. Again, be careful, okay, at 0, because this function is not defined there. So that's what you would have for this one. So that's the first list. And this one, from these, you can create now, and you can combine these parent functions. You can create polynomials, you can create rational functions, and all of those derivatives can be applied if you're going to be doing and applying all the rules. So you can utilize, the actual summation, okay, the actual difference of functions. You can take the product, you can take the quotient, and with all of those, you can create any polynomial rational that you like, okay, out of these. Now, continuing on here, so this one is a little bit trickier. So it's the one parent function, although it's still pretty useful for us in terms of the absolute function. So if you take the absolute of x, okay, so if you recall, okay, so this looks nothing else but just simply like a v. That's how it looks like, touches at the origin, and it has two parts. So you will have, for the x when it's positive, your actual slope is just equal to 1, and this is for all x which is greater than 0. And then for your negative, okay, it's going to be -1, and this is for x which is less than 0. It is not defined at 0. Okay, so if you try to find the limit from the left and the right, okay, you'll see that it just simply does not exist. They do not equate to the exact same thing. So be careful there. This is the 1, and that's anytime you're going to be running into any kind of function which has the absolute over it, it becomes a headache that typically you kind of almost have to spread it into a piecewise function, into two separate ones, and treat it on different domains at the same time. Now, going into these sinusoidal functions, so these two are ones that I relatively remember fairly well. So for sine of x, okay, it's beautifully, the derivative is just cos of x. Okay, so that is the same thing. It's going to be defined everywhere. We do not run into any problems here, although typically we just take one period of this function because it is periodic. Now for cos of x, so the only change now is you throw in a negative in front, okay, but you do get the opposite, so you get negative sine x as your derivative. Again, it's defined everywhere. There are no issues here at all. Now, for your 10x, technically, we wouldn't even have to necessarily add this because 10x is just sine x over cos x. And then you can use your quotient rule, okay, with respect to sine and cos, and you're going to find what the derivative is. I put it here. We can certainly mark it. Just be careful because 10x is not defined wherever cos x, okay, is equal to 0. So we cannot have that at 0. Because 10x is not defined. And for that happens at pi over 2, 3 pi over 2, and any multiple of those. Okay, so if you like, you can write this out. This is going to be true. However, x is not going to be allowed to basically be pi over 2 plus some k pi, where k is nothing else but an integer. So integer we can write with a z or an I. Okay, so this just simply means that happens where cos, if we substitute any of those x's, it's going to give us 0 at 90 degrees and 270 degrees, or as I did it in radians right here. Now, the actual derivative itself, okay, is simply secant squared x. That is the derivative of 10x. And again, you can derive it from just changing 10x into sine x over cos x and using the quotient rule. And this, okay, so now the next set, okay, so cosecant, secant, and cotangent, we can do exactly the same thing. So, for all of these, I can certainly write these out, which I'm going to do so. We just kind of have to be careful that, we don't run into these problems right here, because cosecant is nothing else but simply 1 all over sine of x. Okay, so that's what this equals. And of course, we cannot have sine of x equal to 0, because then it will not be defined. Okay, and where does sine x equal to 0? Well, at 0, okay, at 180 degrees, or at pi, and any multiples of those. So that's one thing that you have to be careful of. Now, writing this out, I like to write this as sine, okay, -1 to the x. So maybe let me, kind of be careful in here so that you don't think that it's the inverse. So here it's going to be to the -1. And now taking the derivative, well, using nothing else but simply the chain. So this is going to be -1 multiplied by, and this is going to be sine, okay, of x, okay, that you have in here. So we're taking this in here. This is going to be -2, and that's going to be multiplied by the derivative of sine x, which is just simply cos x. And that would be your derivative. Now, we don't like to write it this way, so we typically would write all of this right here as simply, so I'll leave the negative out there, so this is going to be cos of x all over, and this is going to be sine squared x negative. That's what it equals. And most of the time, what you're going to be writing this as, because now you have cos over sine, and cos over sine is cotangent, so this is going to be cotangent, okay, of x multiplied by cosecant, okay, of x negative. And that's how you can remember. So this derivative right here, okay, that we're referring to is equal to this right there, and I've just actually proved and derived it for you. So that's what I actually do. You know, if I ever forget, you know, I just simply change it back, and then I will derive the whole thing kind of from scratch, and it's a good exercise for yourself to be able to do it. And don't forget that the restriction still is that, you know, x, okay, as you're going to be plugging it in, it cannot be equal to 0, pi, or 180 degrees, or any multiple of that. All right. Now, for secant, you can do exactly the same thing. Again, be careful of the restriction, because secant is nothing else but 1 over cos x, or, okay, cos x to the negative 1. And again, if you take the derivative right here, what you will find is this is going to be negative, and this is going to be cos x minus 2 multiplied by, and this is going to be negative sine x. The negatives and the negatives cancel, and you're going to get sine x all over cos x squared. And most of the time, this is written out as, okay, so as you can see it, it's going to be 10x multiplied by secant x. That's what this will equal, because it's going to be sine over cos, and then there's an additional cos left there, okay, to provide you the secant. So same thing, I like to derive this if I forget, okay, what it is. So I just simply write it out in this way, and that would have been your derivative. But be careful, it's going to have the restriction where cos x cannot be equal to 0, and that's the same thing at pi over 2 and 3 pi over 2 and any multiples of those, and that is simply 90 degrees or 270 degrees, okay, and again, any multiples of those, okay, both positive and negative. So the last one, cotangent x, so this one, so if you would be doing this, this is cosine x over sine x, and you can now proceed and find out what the derivative of this particular item is, okay? And so for that, if you wanted to do it on your own, you know, you can use the quotient rule, okay, and then proceed from there. Or you can bring the sine x to the numerator, okay, and then proceed from there as well using the product rule. So if I use the quotient rule in here, what I'm going to get is, okay, the derivative of cos is negative sine x multiplied by sine x, okay, from the bottom, okay, and now the quotient rule tells me minus, and now I need the actual derivative, okay, so within the actual sine x, so that's going to be cos of x right there, and that cos of x, so that's from this one, multiplied by cos of x, okay, so that's what you have in there. And what you notice is you can take out the negative, and then you have sine squared plus cos squared, okay, within here, and this is going to be divided by the sine of sine of x squared because of the quotient rule. So again, so negative, so let me rewrite it in here for you. So if you're going to be taking this in, so if I take the negative out, okay, this is going to be sine squared x plus cos squared x all over, and this is going to be sine squared x. Now, this sine squared plus cos x is equal to 1, So this becomes negative 1 all over sine squared x. But what is 1 over sine? Well, 1 over sine, okay, is cosecant squared. Okay, so 1 over sine is cosecant, and because of the squared, all of this becomes negative cosecant squared x. So if you notice, tangent was secant squared x, while cotangent is cosecant squared x, but you have a negative, okay, in there. So that is something that you can remember. I do not utilize these most of the time. I wanted to add these into this video just to show you that you don't have to memorize all of them, but if you're comfortable in taking and using rules of derivatives, you can derive these on your own. Now, the last set, okay, of these derivatives that we have in this, so this one is a wonderful parent function where its derivative is equal to exactly the same thing. It's magical. It's the most beautiful function that there is for anybody who's going to be going into engineering or any application-based, okay, studies of differential equations in the future. If you are one of those students, probably not at the moment because you're just kind of going over grade 12. It's an extremely powerful function which has the derivative identical to it. It's the only one that has that, and it is defined for all x. Now, the derivative right here, if you take bx, okay, so this one has just an added feature that this is going to be ln, okay, of b multiplied by b to the x. So it's not as nice as the e to the x, but it is pretty nice in terms of its derivative, and it is defined, okay, for all x, okay, that we actually have in here. Don't forget that your b is your base, so this is your base, which is going to be between 0 and 1, or it's going to be greater than 1. So those are the actual restrictions on the base that we have. Now, in the logarithm side, so if you were doing these in terms of logarithms, so the derivatives of these, so right here, so ln of x, okay, beautifully is just 1 over x. And now this is only going to be defined for x is greater than 0 because that's what our function is. So we don't actually have negative values of x in here when we're talking about logarithms. And right here, if you take the general log of any base, so this is going to be simply 1 all over ln of b multiplied by 1 over x. So very similar, okay, to the one which is just above. And again, this is for x greater than 0. Now, if it turns out, as you can see there, that your b is any of these, you can, of course, plug it in, okay, and those derivatives are going to be identical, just the b will change, meaning your base. So that is it. You know, if you've got yourself up to this point, okay, this would be your full summary of all the derivatives that you have in here. And again, so I have summarized these in a nice one-page document so that you can download for yourself if you open up the show notes. So it's been a lot of fun, okay, going over these derivatives. So there's probably one more additional video in terms of doing some final derivative applications in terms of examples. Okay, so taking all of these, creating some crazy functions, and then taking the derivatives using various rules. And that's going to be it, folks. Okay, thanks for watching this particular summary. I hope that it helps at least one person. Bye, everybody. Take care of yourself.